Hey there, in this video, I want to walk through with you the assumptions that we make when we run an ordinary least squares regression. For a really good and thorough overview of the assumptions in OLS regression, I would highly recommend reading the Athington article, Back to the Basics, Regression as It Should Be. She does a really good job, I think, of walking through each one of the assumptions in OLS regression and the consequences for violating those assumptions. For full disclosure, Athington was my dissertation advisor, so that's maybe why I'm partial to this, but I think it's one of the best articles really explaining the regression assumptions and kind of the consequences for violating those assumptions. So this document I made is really based off her article there. And so the first assumption that we might talk about is linearity. So we assume that the dependent variable can be expressed as a linear function of the independent variable plus some random error. And at first, this may seem like a pretty restrictive assumption, but it's really just a restriction on the parameters of the statistical model. The predictor variables themselves can actually be transformed. We can take a log transformation of a predictor variable. We can include multiple copies of a predictor variable, like we can include the predictor in like the squared term to assess a quadratic relationship, and this is typically what is done in polynomial regression. What we mean by the linearity assumption is that the actual functional form of the equation is linear, that it can be expressed by a constant and then a coefficient estimate times the coefficient estimate here times your predictor variable, and that these are all added together is what makes it linear in its functional form. So the actual predictor variables can be in whatever form, but that they're expressed as a linear function of one another is what that assumption really means. So the next assumption here is specification. So we assume that the model is correctly specified. In other words, that we've included all the relevant independent variables in the model. You might hear this also called like omitted variable bias, that if we omit an important predictor variable, then that biases the coefficient estimates for the other variables in the model. The no measurement error assumption here, we just assume that all the independent variables are measured without error. You might hear it called that, we assume that the predictor variables are treated as fixed values instead of random. You might also hear this called weak exogeny. The consequences of both of those is that the independent variables, the fact that they are treated as fixed is that they're measured without error. This assumption is typically violated to some degree, especially in like the educational, social, behavioral, psychological type sciences. And so the consequences of this assumption depends on if the measurement error is occurring in the dependent variable or in the independent variable. If the measurement error occurs in the dependent variable, our coefficient estimates will still be unbiased, but the estimate will become less precise. The standard errors will actually increase. Now, if the measurement error is in the independent variable, it will attenuate the effect for that coefficient estimate, so it'll actually bias the coefficient estimate towards 0. So the remaining assumptions here are really concerned with the error term, or maybe you might hear it called like the stochastic part of the regression model. So we're concerned with these errors here in the So formally, we assume that the errors are normally distributed with a mean of 0 and some constant variance that we're labeling sigma squared here. So we assume that the errors have a mean of 0, calling this mean independence. So we assume the error term is 0, and this value doesn't depend on any of the independent variables. So this assumption is typically violated when we omit an important predictor variable, since those effects lump into the error term. It's also violated when we have nested or clustered data. So the classic example of nested data in educational research is students nested within schools. So the idea is that students within the same schools share are more similar to each other than students in different schools. And so students within the same clusters, or so in this case, students within the same groups, share many similarities. So students within the same schools typically come from the same communities. They have the same set of teachers. They share the same sets of resources. And so this can have the effect of biasing our coefficient estimates. And we'll talk in the regression diagnostics about what can we do for this. You could use an alternative modeling strategy that takes into account the fact that takes into account the nesting. You could actually just model an effect for each one of those groups. So there are several ways that we can deal with this violation. But so we assume that the error term, that the errors have a mean of 0 and don't depend on any of the independent variables. Homoscedasticity, this is also called our assumption of constant variance. This is the same thing that same assumption that we make in like an ANOVA model, the homogeneity of variance. We assume that the variance of the error term is the same across all levels of our independent variable. That's why we call it a constant variance assumption. So if this assumption is violated, typically the standard errors are going to be biased. Often they're biased upwards. And typically if you violate this assumption, it's usually an indication that some other assumption in your model is violated. And we'll talk about that some more in the regression diagnostics. But we can also make some adjustments. Usually this affects the standard errors of the model, and so we can make an adjustment to the standard errors using what they call like heteroscedastic consistent standard errors, or robust standard errors, or Huber-White standard errors. They have lots of different names for the same thing. So we assume that the errors have a constant variance. Right, same idea as the homogeneity of variance in ANOVA models. We assume that the errors are uncorrelated with each other, right? They have a covariance of 0, so that the value of the error term for any one observation is not influenced by the error term for another observation, right? The errors are uncorrelated. So this assumption is typically violated when observations are correlated across times, or again when we have sampling clusters like the nested data, or we've omitted an important predictor variable. Because if that omitted predictor variable is then correlated with another one of our independent variables in the model, that will then cause a correlation between that predictor variable and the error term in the model. You might hear this also called like endogeny in econometrics literature. They're talking about the same thing, that the errors are uncorrelated with each other or with one of the predictor variables. Some fields sort of combine these. They may combine the mean independence and this uncorrelated error term, and they call it like strict exogeny. and they're it's all meaning the same thing, that the errors are uncorrelated with each other and that they're uncorrelated with any of the predictor variables. Violating this assumption will typically have a consequence for the coefficient estimates and the standard errors. If we're omitting an important predictor variable, then that's going to bias the coefficient estimate for any of the other predictor variables that are correlated with that omitted variable. We assume that the errors are normally distributed, that the distribution of the errors is normal. This is generally not a problem the larger the sample size we have. And if this assumption is true, then the OLS estimator is a maximum likelihood estimator as well. Some other things to keep in mind, you might hear these called assumptions or not, is we can't have perfect collinearity, so one independent variable can't be perfectly correlated with another independent variable. There's no solution. So you can't have an exact linear relationship. We also don't want high correlations among our independent variables. We'll talk about this as like multicollinearity, because that causes a problem in interpreting the results for those variables that are highly correlated. We can't disentangle the effect of those results. Now, multicollinearity is really a problem when we're using regression for explanatory purposes. Now, if you're using regression purely for predictive purposes, and you don't want to then go back and interpret what these coefficient estimates might mean or relate them back to inform some theory, multicollinearity isn't a problem. And it could, it's not a problem in the estimates, but it's a problem in the interpretation. So depending on how you're approaching OLS regression, you may or may not hear about this issue. The dependent variable in OLS regression should be continuous, so it's measured on an interval or ratio scale. Although it's possible to produce coefficient estimates or estimate a model for a dependent variable that's not continuous, you could incur some other issues, like the predicted values might be out of range. So if you have a censored dependent variable or it's truncated on one end, you could get predictions that are actually out of range for that. So it might limit the functionality of the model. We also assume that the sample is a random sample from some population of interest. So this is very important if we want to make generalizations back to some population, right? We should have, our sample should be a random sample from that population. So why do we make such a big deal out of OLS regression, the OLS regression coefficients? It's really because of this Gauss-Markov theorem, which states that the OLS estimates are the best linear, unbiased estimate of the regression coefficients. So in other words, the OLS estimates have the lowest sampling variance of any linear, unbiased estimator, if certain conditions hold. So if the errors in the linear regression are uncorrelated, have an equal variance, and have a mean of 0, right? So if the OLS estimates are unbiased, they're actually the best linear unbiased estimate. If the error terms are uncorrelated, they have a constant variance and a mean of 0. Notice it says nothing about the error terms being normally distributed, right? Only that they're uncorrelated with the mean of 0 and a constant variance. The normality assumption is really convenient for making statistical inferences about the model, but it's not necessary for the coefficient estimates to actually be unbiased. You might hear the regression coefficients. You might hear they might be called they're blue sometimes, and that's just an acronym for this best linear unbiased estimate. So in the class of linear unbiased estimates, the OLS estimators have the lowest sampling variance. That's what makes them so-called the best. So what are then the implications for other types of estimators? So say in like linear mixed models or multi-level models, we typically estimate random effects with what's called an empirical Bayes estimator, or you might hear them called like a shrinkage coefficients. It means that those coefficients are biased estimators, right? And in this case, the empirical Bayes estimators it's biased because it's actually pulled towards the grand mean in that case. But the reason those are preferred in that situation is because they're a more efficient estimator. They have a lower mean squared error. So that's when we talk about the OLS estimates are best in the class of linear unbiased estimates. So as long as the errors are as long as the errors are uncorrelated, have a mean of 0 and a constant variance, the OLS estimator is an unbiased estimate of the population parameter. A couple little fun poems to help you remember the Gauss-Markov theorem. Roses are red, the OLS is blue if Gauss-Markov is true. Or, roses are red, the OLS estimator is blue, and I like running regressions with you. So just a couple things kind of help you remember the Gauss-Markov theorem and what it says for OLS regression. So in the regression diagnostics model, we're going to run through some different ways of assessing these assumptions, and they're usually assessed with plots of our residual terms. And so the residual in regression analysis is our predicted value. So what's our model's predicted value if we input each one of our regression estimates, our coefficient estimates, and then the values for each one of our independent variables? What's our estimated or predicted value? The residual is the difference between our actual value for y and the predicted value, and we'll assess whether some of those residuals then seem to meet some of these assumptions. So here's just some example. For the linearity assumption, we might plot then our fitted values against the residuals, and if we want to see a random scatter. Usually no pattern in the residuals is an indication that the model assumptions are tenable. And if we start seeing a pattern in the residuals is when we start to get concerned that some of the assumptions may be violated. So in this scatter plot might suggest that the linearity assumption has been met, while this scatter plot over here seems to suggest there's some nonlinear relationship that we're not accounting for in the model. See how the residuals tend to make like a quadratic curve here? That suggests that one of our independent variables should maybe be modeled with a quadratic or squared term in the model. We can use a QQ plot to kind of assess that normality assumption. So on a Q, plot the observed values of the residuals against a theoretically known distribution, so like a normal distribution. And these quintile plots assess it on like a 45, so they place a perfect normally distributed residuals would fall along a 45-degree angle here. So notice that these dots all fall along that 45-degree line, which seems to suggest that the normality assumption has been met, while these veer far from the line, which would suggest the normality assumption has not been met. We could also use the plot of the fitted values against the residuals as an indication of the constant variance assumption. Again, this is where no pattern indicates that the assumption has been met. So we'd want to see that the residuals are evenly distributed across all of the fitted values of the model. That means that the variance in the residuals is constant across all of these fitted values. They seem to be stable across each fitted values. While here we see that these residuals are sort of making a cone shape. We see they're making a cone shape like this. They're fanning out. That's then an indication that the constant variance assumption hasn't been met. Whoops. So we'll talk about these more when we go through the diagnostics module. I just wanted to give you a walkthrough of what the OLS regression assumptions and what do they mean when we talk about that the error terms are normally distributed with a mean of 0 and a constant variance. You can kind of get an idea of what we're talking about there. You know, as always, if you have questions or concerns, please email me, and I'm happy to chat with you more about it. Thank you.